You should be able to see my screen.
Yep.
Okay, good. So, um, so two announcements. Okay, one is that so let's write out announcements. Gotta have some of those. So the first is that homework 3 goes out today. And it's shorter than the previous homeworks and hopefully also easier. And it's due on the last class day, which is literally the last day I can actually ask you to do anything for me. So it's due basically at the deadline. So that's announcement number one. And to make it a little bit more fun, I have ordered for us, SOS caps. You're all, well, Akash excluded because he's not in Pittsburgh. I'll save your, I'll save your hat with me, and I'll give it to you when we meet, Akash. But
Thank you very
um,
much.
yeah, I'm hoping that this company gets back to me quickly and makes his hats, and it's gonna be our something to remember this class by. Good. So look for your pseudo expectation hats. I guess it should be the other way around. Being a bit Yoda-esque. Okay, good. Those are the announcements. And so let's begin. So I realized that if all I wanted to do was like do more algorithms, then I could go on for a little bit more. But I thought, given that we are in the penultimate lecture, it's good to go back and take some kind of a take somewhat of a broader perspective. And so we'll do that today. We'll actually study the relationship between what I'll call spectral algorithms and the algorithms based on sum of squares. We'll still do algorithms because we'll still prove some cool theorems and still design some cool algorithms. But we'll take like a broader view, and try to find out this relationship between sum of squares and spectral algorithms. Okay. We'll kind of continue this investigation of simpler algorithms related to SOS. So today we're going to look at spectral algorithms, and in the final lecture, we'll look at even simpler algorithms based on low degree polynomials, and all of this hopefully should become clear later on. But that's basically our plan for this and the very final lecture. Cool. Let's begin. So, what have we done so far? We looked at a bunch of average case problems and designed algorithms for many, many of them. Um, if we go back and look at these problems, actually we can split them into two broad categories based on the distributions of instances that we considered. Okay, so the first category I'm going to call refutation problems. And at a high level, these problems get input from some distribution D. So input instances are chosen according to some probability distribution. And for whatever problem we are looking at, with high probability, an instance drawn from this distribution happens to be a no instance, as in it does not admit a solution. Okay. And in fact, I'll start using the terminology null instance or null distribution to talk about no instances. Okay. Just because it's a more fun term to use. And the goal in such problems, because there is no solution, the goal is, of course, not to find a solution, but to prove that there isn't one, to find a certificate that you are indeed a no instance. So the goal, the algorithmic goal, is to efficiently find a certificate of there being no solution. My fan is making noises, so I'm going to kill other programs before it kills our program. Oops. Okay, good. Continuing. Good. Yeah. So if this kind of surprised you, or if this has gotten you confused, then notice that the example of this problem that we spend some time on is this problem of refuting random CSPs. So if you remember, this problem, if you remember this problem, it was basically given a instance of, let's say, XOR CSP, where each constraint is chosen at random. We take enough constraints so that so that the instance is unsatisfiable with high probability. In fact, we take enough constraints so that no more than about half the constraints can be satisfied by any assignment. And then we ask the question of finding an algorithm that can certify this for us, that can give a proof that the instance is unsatisfiable. And when we proved Gregorius theorem, we proved in fact that at least sum of squares can't help you do it. When you only have linear number of constraints, right? And that's what we spent some well, I guess at least one lecture on that proof. So that's an example of this this kind of a problem. It's a problem where we have a distribution on instances of a problem, and with high probability the instance is a no instance. It does not have a good assignment that satisfies all the constraints or even most of them. And our goal is to efficiently produce a certificate of this fact, right? That was an example. Very good. The other bulk of problems that we saw were what I'm going to call planted problems. And what are planted problems? Well, it's still an average case problem. So the instances are still chosen according to some distribution. But this time, with high probability over the draw of the instance itself is going to be a yes instance. As in, whatever we call solution for the purpose of that problem, such an instance would have a solution with high probability. Okay, and that's basically what I mean by this planted part. There is a planted solution, if you will. Okay, and the goal is to find it. Well, actually, let's call it find a solution. There can be multiple. And so literally everything we did in the last 4 to 5 lectures is an example of, a planted problem. So example, tensor decomposition. At least tensor decomposition when the components of the tensor are, chosen uniformly at random. That's, one example of a planted problem where the solutions are really the components of the tensor. Okay. But what else? Literally everything can be interpreted, in this fashion. So for example, this problem of Gaussian mixture clustering, the solution were the unknown planted clusters, unknown, original clusters. And we designed a whole algorithm to, approximately recover the clusters. Okay. And so, good. Okay. That's the classification I want to, just remind you of. Like, these are the two kinds of problems that we saw. And actually, today we will also spend time on a third kind of problem, which I'm going to call distinguishing problem, which is kind of related to both these problems above. Okay. What's this problem? Well, now in this case, there are two distributions. Okay. Let's call it D planted and D null. And so the terminology should kind of make sense to you. D null would be a distribution on no instances, or with high probability no instances. D planted would be with high probability yes instances. And what you're going to get is an input instance which is chosen from one of these two distributions. I'm going to press one button, and it outputs a coin toss. I use, deplant. If I get heads, I'm going to sample from deplanted. If I get tails, I'm going to get a sample from denull. And once I've tossed this coin, I'll just press another button to draw a sample from deplanted or denull. And so it's is chosen is either a sample from deplanted or denull, and the goal is to tell which is which. Okay. We haven't talked about these problems at all, but when you try to view average case problems and try to like somehow cook up a good theory to think about these problems as a whole, then it's good and useful to think about this third problem in addition to the refutation and planted problems that we saw before. Okay, so we'll keep this like classification in mind. We're gonna come to why this classification matters, etc. As the class progresses, well, this and the next class. um for now, we'll actually just dive into an example, because we've got to do some math to feel interested. We got to prove some theorems rather than just give definitions. Good. So what's my example for today? I'm going to actually do two examples. Example one is going to be the max click problem. Okay. Now, what do I mean by that? I'm going to construct a planted version of this problem, a null version of this problem, and a distinguishing version of this problem. Okay. And we're going to explore each of them and design algorithms for each of them and talk about and pontificate about each of them. Okay. So let's talk about the refutation question here. Okay. And here's the distribution I'm going to consider. My D null is simply going to be a graph drawn from G and half. So you all remember G and half. This is the distribution on graphs where, all the graphs have n vertices and each edge is chosen to be in the graph independently with probability half. Okay. So I hope, this distribution is one of your favorite distributions because it is mine. And, what am I concerned with? Well, I'm concerned with what's the size of the maximum click in a G drawn according to G and half. Okay. Of course, with high probability, that's, I mean, yeah, so there's a distribution. So all the facts that we are looking for today are, going to be with high probability. So the question one is, what's the size of max click in G? By the way, I don't know if we ever the class is becoming a little bit of a blur for me because I keep talking about the same things in and out of the class. So now I forget if I ever, we did clicks or anything like this. So, hopefully this question is new to you. And you all remember what the click is. And, pardon me if I've already told you a bunch of times what this is. Let me remind you nonetheless. So click is just a collection of vertices such that, every pair of them has an edge between them in G. Okay. That's what a click is. Okay. So a pair, it's a set of vertices such that all pairs are connected in G. So that's a click in G. And so the question I'm asking you, what's the size of the maximum click in G? And that's my silly question number one for today. So time to unmute yourself and tell me, what do you think is the size of the maximum click in G?
It's like 2 log n with high probability.
It is 2 log n with high probability, Misha. That's correct. You win a hat. Well, I guess everybody wins a hat. Yes, and Misha is absolutely right. The max click in G is gonna be of size 2 log n. Now, in fact, this is one of those really crazy probabilistic statements. Um, um, Actually, this statement itself has a pretty nice history. Um, this fact was first proven by Bolobash sometimes in the 70s. And I feel like I've gotten the accents wrong. There is probably some accent here. Let's just go with it. And, it's like actually the statement is really strong. So what the real statement says, which is really not, somewhat peripheral for us, but, it's still good to point it out. It proves something called as a 2-point concentration. So it turns out that, with like, 1 minus little o of 1 probability, so like let's say 99.99999% probability, the max click in G and half has size 1 out of 2 possible numbers. And that those two numbers happen to be, the floor of 2 log n and the floor of 2 log n plus 1. Okay, so basically, this particular statistic exhibits a extremely strong concentration. It's not just expectation. It doesn't just have expectation 2 log n. In fact, it's very tightly concentrated on just two values. Okay, and like there are a bunch of graph parameters which have this really strong concentration, and some really cool probability goes into establishing this. But as I said, peripheral for us. Good. Actually, to see that 2 log n is the right number is not so hard. Let's maybe, quickly sketch it. Sketch for y. At least y you would guess this number is not so hard. So like imagine that, s is a set of size t. Then what's the chance that s forms a clique in G? So chance that s is a clique is 2 to the minus t choose 2, right? Because there are t choose 2 edges, and each of them is chosen independently to be in the graph, and so all of them are present with probability 2 to the minus t choose 2, right? And so now if you calculate, let's say, expected number of clicks, then it's going to be n choose t, which is basically the set of all possible choices for t size subsets, and then 2 to the t choose 2, right? And so let's just examine this expectation expression. I'm going to spend like 30 seconds on it. So it's like about n to the t over t factorial, 2 to the minus t squared over 2. I'm going to ignore, this, t versus t minus 1 difference, and I'm going to ignore like n times n minus 1, etc., and n to the t difference. And, this expression looks like 2 to the minus t log n, oh, sorry, 2 to the plus t log n, 2 to the plus t log n minus t log t roughly, and minus t squared over 2. And so this expectation becomes less than 1, less than 1 if if t squared by 2 basically matches t log n, and that happens when t is 2 log n. And so that's some simple heuristic to at least guess why 2 log n might be the right number. Okay. So yeah, I'm not going to prove this Bolobash's theorem for you today, but that's what we'll take away. Good. So conclusion from our discussion so far: max click in G is at most 2 log n. Actually, for our purposes it doesn't matter. So in fact, I'm going to be even rougher: order log n with probability 0.99. Good. So now what? So I said, this is d null. This is, no instances. So we should define our solutions in a way that, this graph does not have a solution. So what should be my concept of a solution? Well, think of a solution as a clique of size, I don't know, bigger than 3 log n. Then, with high probability from our discussion right now, G chosen from G and half, does not have such a solution. Good? Still with me? Very good. And so now, I can define a natural refutation problem here, right? What's the refutation problem going to be? So this, I'm going to do the same trick that we did to formally define what a refutation problem should mean in the context of CSPs. A refutation problem means that you need to find an algorithm. So, give an algorithm that takes input an arbitrary graph G, let's say on, n vertices. Okay. And outputs some value, some number V. Okay. You can make it integer if you like, but doesn't matter. And the correctness property is that V should be bigger than, max click of G. So, I should always output an upper bound on the max click. Okay. And just like if you remember what happened in the context of CSPs, so far the goal is extremely simple to meet. You can simply take a graph and output n all the time, and that's going to be a valid upper bound on the max click of G. But of course, we're going to make it a little bit more interesting, and that's the only place where the distribution of G comes in. So we would like the probability that when G is drawn from G and half, our null distribution, V is small, let's say smaller than some parameter omega, is 0.99 for as small an omega as possible. Okay. And for whatever omega, there is a, let's say, polynomial time refutation algorithm. I'm going to call, that, I have a solution for the omega refutation problem, if you will. Okay. So the question we are investigating is the refutation problem, the refutation question now. For what omega does there exist an efficient, and by efficient, will mean polynomial time, uh, um, refutation algorithm for max click in G. Good. So let's maybe first, forget about the efficiency constraints. What happens if I allow you to give me a algorithm that runs in whatever amount of time you might like? What's the omega for which I can actually construct a refutation algorithm and guarantee all these properties that I would like? Silly question number 2. So feel free to unmute yourself.
2 log n.
Right, exactly, right? Like I I can't defy reality. If I go below 2 log n, then the third condition is going to be just impossible to satisfy because the truth is against us. And so if we want this goal to be at all feasible, then omega better be at least 2 log n. So note omega at least 2 log n. And so the question is how close can we get to this lower bound, right? Okay, good. So Jeff, given that you answered this, maybe you also want to describe what is the brute force algorithm you have in mind.
Oh, like fix your omega and then look for all subgraph of omega vertices and then check if it's a click.
Right, absolutely. So the refutation algorithm Jeff has in mind is the following. Take this parameter omega that you're trying to construct a refutation for, go over all possible subsets of omega size of vertices. And check if there is a click on those vertices. And if you fail to find a click on all possible subsets of omega size, then just return that you have refuted, because you've given a certificate. The transcript of this brute force algorithm is a certificate that there is no omega click in G, right? And so you can hope to succeed for a random graph G drawn from G and half whenever omega is, let's say, 2 log n plus 2, for example. Right? Good. Still with me? So what is the running time of this algorithm? Well, because you're going to run it for, like, let's say omega less than 3 log n, the running time of this algorithm is like upper bounded n to the O of log n, right? So in fact, this brute force algorithm runs in time n to the O of log n, right? And our question is, well, what if I do not allow you n to the log n time? What if I only allow you n to the O of 1 time? What's the best you can do? Okay. Good. So now, so this is the problem we'll talk about today. Well, in part. And the nice thing about this example is that now I get to introduce to you the word that I use in the title. So now what we'll do is, we'll study a spectral refutation algorithm. Okay. And let me, play spoiler right away. The algorithm I'm going to give you is effectively the only and the best polynomial time refutation algorithm for this problem that we know of. Okay. So hopefully this gets you exciting because I'm going to tell you the best possible algorithm in the world for this problem as far as we know it. So let's see. Okay. So what's but before we go ahead and do it, I want to maybe like focus a little bit on this word spectral refutation. What does it mean? Okay. So a spectral refutation algorithm does the following. Okay. So again, it's going to be a slightly meta mathematical definition. But given that I'm going to call it as a class of algorithms, it's important to at least give a meta mathematical or at least a vague definition of what I mean by it. Okay. So what's a spectral refutation algorithm? Well, it takes input. So in our case, it takes input this graph G. Then it is allowed to build in polynomial time any polynomial size matrix that depends on G. Okay, because I'm asking you to build this, a matrix in polynomial time, and I want you to write every entry down. Okay, so I'm not allowing any cheating representations where you give me some, weirdo thing where you allow me to compute entries of M, but M might be huge. No cheating allowed. You to give me M explicitly, you to write it down for me. And so, because I'm giving you only polynomial time, this M can only be of size, polynomial size, right? Its dimensions have to be polynomial. So, let's maybe index its dimension suggestively by some number D, which will pretend we haven't heard of, but D eventually will become degree, the degree that, we played with all through this class. So let's say, it's n to the D by n to the D for some D, which is O of 1. Okay. So it's a polynomial size matrix. You're allowed to build any such matrix. Okay. So build a matrix, to your heart's content and, relate the value, let's say, of max click that we care about to, the largest eigenvalue of M. Okay. And step 3, output, well, the largest eigenvalue of M. And the point is that if you look at, step 1, if we built M of G in polynomial time and we are computing the largest eigenvalue of M, then, the whole algorithm that I'm running is a polynomial time algorithm because, largest eigenvalue of a matrix can be computed in polynomial time, in the size of the matrix, right? And so if step 2 is correct, as in we were able to relate the max click size of G to, the largest eigenvalue of this, matrix M of G, then, we'll actually have a certain refutation algorithm, right? How good it is, etc., is, all, up to our analysis and building M of G. But this is an outline of a spectral algorithm, right? In general, a spectral algorithm builds a matrix out of input efficiently and computes the largest eigenvalue. So when you apply spectral algorithms to search problems like solving planted problems, you might actually not just want to compute largest eigenvalue but also largest eigenvector. And usually you can use this largest eigenvector to solve the planted problem, like recover the solution, etc. Okay. And let's not focus on that because that's not going to be of our interest today. Let's just focus on the refutation kind of question, and then we'll just be interested in computing the largest eigenvalue. Okay. So hopefully at least vaguely this notion of a spectral algorithm is clear. Okay, good. So now let's design a spectral algorithm for refuting max click. Well, I'm going to use the simplest possible matrix. In fact, everything I'm going to do today is going to be simple. So what matrix? Well, I'm simply going to use the plus minus 1 adjacency matrix of G. So my A is going to be an n by n matrix. N is the number of vertices in the graph G. and aij would be equal to plus 1 if I is connected to j in G, and minus 1 if I is not connected to j in G. Okay, so this is the plus minus 1 adjacency matrix. And now, so, well, that's a step 1. And notice that I can compute this matrix given a graph in polynomial time. Um, okay, the less that I say about it, the better. I hope you all see that. And next, we want to relate the max click size in G to the largest eigenvalue of A. So let's try to do that. Okay. So suppose X is a 0, 1 indicator of a subset of vertices. So it's an indicator of a subset of vertices, right? Now suppose X indicates a click in G. Okay. Then what should happen? Well, if X indicates a click in G, let's try to understand what happens to X transpose AX. Okay, where A is this matrix that we just defined. Well, if now I sum over all ij, so this is just a definition of the quadratic form. Now notice that if X is indeed an indicator of a click, then aij is going to be 1 whenever xi and xj is 1, right? Which means that I'm going to get, oh, and okay, so maybe I'll write it down and then talk about it. So what do I really get? I get some xi square, and then I'm going to subtract out some xi square because the diagonals of A are supposed to be 0 because it's an adjacency matrix. Okay, I mean there are multiple ways to define it, and I could simply just have um, label the diagonals of A as -1, assuming that there are no self loops. But let's do it this way. It doesn't matter. Okay. So still with me? Still makes sense? Okay. So notice that if X indicates a click, then this is what I know, and now I can use this equation to do the following. So so this I guess is observation maybe 1, and observation 2 is that X transpose AX for literally every X in the world is at most the L2 norm of X times the largest well, the spectral norm of A, or the largest eigenvalue of A, right? A is a symmetric matrix here, so it's the largest eigenvalue of A2. Still with me? Still makes sense? Okay, so now I can apply this reasoning to the vector of the click, right? The indicator of the click, and use that sum xi square minus sum xi square is at most okay. So this is just combining star and maybe double star. Okay, and now you see we are actually winning this because well, this thingy is simply sum xi square, because that's what L2 square norm is, right? And so I can just divide by some xi square throughout and obtain, and notice that I can square, because xi was supposed to be 0, 1 on the left hand side. I can square without any ramifications to me. I divide by some xi square and I get some xi square, 1 copy remains, -1 is at most, or and notice that for a 0, 1 vector, this is simply equal to the size of the click. Okay, and so what have we derived? We have proven to ourselves. So conclusion, Okay. So, we have done step number two. Step number one was constructing this matrix. Step number two was, proving that the spectral norm of, this matrix of the graph gives us, an upper bound on the max click in G. And we found that result. And so now, we've done our algorithm. Like we at least have a refutation algorithm. We don't know how good it is, but we have a refutation algorithm because we're just going to construct this matrix A and return its spectral norm, right? So refutation algorithm, return. This is what we are going to do for every graph in the world, okay? There is no randomness right now. What we've established is that the spectral norm of A is just simply an upper bound on the maximum spectral norm plus 1 is an upper bound on, the max click in every graph in the world, okay? And so we have satisfied the correctness property. We have satisfied, efficiency property. We have a polynomial time algorithm that always outputs a correct upper bound. And so now, we want to question, we want to understand, what is the typical value that we return on, a graph chosen according to, a G and half distribution, right? So the question is, how good, i.e., how small is the typical omega is the algorithm. Okay, so let's look at this, okay? So let's make a claim. Suppose G is drawn according to G and half, then with probability at least, let's say 0.99, A2 is O of square root of n. Okay. Now I'm sure that, many of you might have seen this kind of stuff before, but,
Actually,
still fun to
Prabir,
do. Yeah.
this was on homework 0, by the way.
Oh, it was?
It
Okay.
was
Well,
it was the bonus question. I think the other question we had you guys prove it's like less than, it's like n to the 0.9 or something like.
this particular question. You mean this particular claim, right?
This particular claim, yes, this exact.
Good. Yeah. No, I was not gonna approve it, but it's good to recall that we or you already proved it on homework 0. Homework 0 has never left our side, right? Like it's been a whole semester and we are still referring to homework 0. How great is that? Um, proof homework 0. But okay, let's facetiously, let's just think a little bit about this. Um, Actually, I want to maybe do a proof of this in a way that I'm going to use it again, and I'm going to give a I'm going to give you kind of a worse proof because it will give a slightly worse bound than this up to some polylog factors, but it's going to be useful to us. Okay, so let's see this worse proof. Well, this you already proved on, or at least you proved n to the 0.51 on the homework. This, by the way, is a really cool random matrix fact. So let me actually, so this is random matrix theory. It's a very basic one. Let me state a fact which I won't prove, and then give like a weaker proof which I will do a proof of. So the fact is, suppose that let's call it M. Suppose M is a n by n matrix. Let's say that it is symmetric. So, Mij equals Mji for every ij. And all entries in the upper triangular part of M are independent. In the upper triangular part, just because, by symmetry, the lower triangular part is completely decided by the upper triangular part. So, let's say the upper triangular part, consists of independent random entries. And now, I want to talk about the distribution of these entries. So I don't really care about what the distribution is. Suppose further, I only care about like some basic facts. Suppose further that each such entry has mean 0. Let's say variance at most 1. Okay. And fourth moment, so let's call it, that's what I mean by fourth moment, is, uh, some constant. Okay. Then, okay, so this is a cool fact, and you can prove it with there are like several proofs of this. And if you haven't seen this fact before or haven't done a proof of this, let me point you to please read Terry Tao's blog post on this because it is excellent. If you search for like Tau operator norm concentration, that's what you will get. And so check it out because it's really cool. And like he gives like 4 different proofs of this fact. um, in fact, the last proof gives precise constants here, so you can in fact determine these constants extremely accurately. But that's not our goal today. So that fact actually completes the proof of refutation. To be honest, it basically gives us a refutation algorithm. Actually, maybe let's interpret that for a bit before going into the proof of this fact. So so what have we done? So take a step back and observe. There is a refutation algorithm for max click on g and half with omega equals order root n. Okay, so I'll tell you a little bit about the proof because we want to talk about it a little bit more, but maybe let's understand what we've done. So the true maximum click in G was of size 2 log n, right? And we've come up with an algorithm which gives us a refutation for omega equals root n. So in some sense, in English, you can think of this claim as saying that you can only certify to me that g and half has no click of size bigger than some c root n for some constant c. You can't even prove to me by what we've done so far that there is no click in g and half of size n to the 0.49. Even though of course there is no click in g and half of size like 3 log n, you can't even in polynomial time prove to me that there is no click of size n to the 0.49 in g and half. Okay, at least by what we have done. But as I told you earlier, this also happens to be essentially the best known algorithm we have. I'll tell you a little bit of an improvement in a second, but basically this is essentially the best, literally best we know, if you stick to polynomial time algorithms. And so what we have actually found out, it's maybe good to add this word to your vocabulary or phrase to your vocabulary. It's an example of an information computation gap. So what does it mean? It's some slightly fancy terminology for the following simple phenomenon. There are various situations in average case complexity, when you're trying to solve average case problems, that there is some parameter that you're after, like max click in G in our case. And the information theoretic optimum value of that on the distribution you're working with is some value. So for in our case, it happens to be 2 log n. But the best algorithmically certifiable bound that we have is miles different from this particular value. There is a gap between what is information theoretically true or what is true without computational constraints versus what you can actually prove when you are um, um, constrained by polynomial time computation. And so there's actually a whole sequence of problems that you study in this there's like a whole study of information computation gaps in this area. And the question is, are these gaps real? How can you ascertain them? And um, well, all kinds of investigations about this, but as you can imagine, they're kind of important. And what we've seen is like because what we've seen is essentially the best possible algorithm that we know for this problem. We've actually found one example of an information computation gap, namely in the context of max click in G and half. Okay, so let's pause for a second and see if there are any questions before I go ahead.
So starting with this matrix, we already have no hope, right? I mean, the max singular value will be at least square root n minus 1 anyway.
Exactly, yeah. And so that
we can't hope omega to be better than that.
Absolutely.
Using this matrix.
So Pranit is right, and Pranit is hinting at the Praneeth is hinting at this issue that at least if we are forced to use simply this particular matrix, this plus minus one adjacency matrix of the graph, then there is literally no hope. Okay, so let me switch orders a little bit and show you a better matrix before proceeding to do a weaker proof of this fact. Okay, so let's answer Praneeth's question because that seems like a more interesting thing to do in this context. An improved algorithm. Okay, you'll see what the improvement is in a second. Okay, but here's what I'm going to do. Okay, suppose, so take any subset of size n, a subset of size, some parameter t, okay, of vertices. Okay, and for every s, define the following matrix.
So Pravesh, are you looping over S? You said for every S.
I'm just defining things right now. I haven't given you an algorithm at all. I'm just gonna like give you a definition, play with it, and then make it an algorithm. So let's say a sub s at I comma j equals +1 if s union ij is a clique in G. Okay, so remember what it means. It means that all pairs of vertices within S have an edge between them, and I and J have an edge between them, and I and J have an edge to every vertex in S. I want to think of it this way because it's kind of helpful, maybe. Okay, that's the visual representation of when this edge exists. Otherwise, I'm going to call it, let's say, -1. Good. Okay. So now what? So suppose X is a clique in G that contains vertices in S. Okay, so X is a clique, or X is an indicator of a clique, to be honest, and it is a clique that includes all the vertices in some subset S of size T. Okay. Then I want to claim X transpose AX. Wait. Actually, let's write it this way. X transpose A sub X X, I want to claim, is equal to what? Let's understand what is it equal to, okay? Now, A sub S, only has edges between pairs I and J, okay? You know what? Maybe it's easier if I only define this matrix on n minus t cross n minus t. And by that, I mean, I'm just basically removing the vertices in S. So I and J will always be, I and J will always be vertices which are not contained in S. Okay. So now let's understand what this expression looks like. If X is a clique, right, and it contains the vertices in S, then this particular this particular quadratic form really counts the number of edges. So okay, let's maybe draw a diagram. So you have S here. Now you have all possible vertices, other than S here. Okay. And so what does X transpose A sub S X count? Well, it equals sum over ij in n minus s xi xj A sub s ij. And so this really, is equal to the number of edges in the set indicated by X, minus S, right? And which equals the number of vertices in S minus the size of S. It's really, choose two, but oh no, oops. Make sense? Okay, so now, let's do the same trick that we did earlier. Okay, upper bound is A sub X by, the spectral norm upper bound that we used earlier. Okay. And for at least so remember that here X is the indicator of a clique that is supposed to contain S. Okay, we are only doing this upper bound for this special subset of vertices. Nevertheless, I can now just like rearrange this equation to get the following. So what do I have? I have x2 to the 4 plus s square minus good. And now, just like before, I divide by x squared throughout to get and so, this allows me to conclude still makes sense. Okay, but now notice that if I repeat this reasoning for all possible subsets S of size T, all possible subsets of vertices S of size T, then I can derive the upper bound. Thus, for all clique indicators, it's true that 2 times max over S of size T right? Because it's got to contain some subset. And so I'll just do this argument for that particular subset. And if I take max, then I have an upper bound that that holds true for all possible clique indicators. And so now I have gotten a different upper bound. Namely, this time it is not a single matrix that I'm computing. It's actually, n to the t different matrices. So we've constructed and let's look at the distribution of entries of A sub S. Okay, to see if so the question is this a better upper bound, right? So the bound we are getting is like 2 times t plus the maximum possible spectral norm of any A sub S. So the question is it a better upper bound? So let's understand the distribution of entries in A sub S. Okay, first of all, most of the rows of A sub S are actually going to be 0 in the graph G. Can someone unmute themselves and tell me why? So no, so let's understand, when is the ith row, when is this ith row non-zero? Well, only when S, S union I is a clique, right? In other words, I needs to have an edge to all possible vertices in S. Still good? And so what's the fraction of sorry, was it a question?
Yeah, question. Wait, so I thought it's either like the entries of AS are 1 or -1.
Oh, yes, which means that good, you are right. Sorry, let me modify. I guess this one would probably work too, but you're right, Alice. I think I analyzed something else and defined something else. So +1 if I is connected to J, -1 if I is not connected to J, and S union IJ is a clique, and S union IJ is a clique, and 0 otherwise. Okay, so my question was bogus because I did not even define the matrix correctly, but now I did. And let's maybe make sure that the analysis was right. Well, I guess, yeah. I'm glad I fixed this definition because this fact is not true. Well, I
If I
guess
and J
it's
are
still an
not
upper bound. It's not
connected,
true if I didn't define it this way. Sorry, what was the question?
if I and J are not connected, how can S union I comma J be a clique in your definition for -1?
Yes. So I guess I'm still not getting it right. So let me be. I guess here's what I want to say. I want to say that I is connected to all possible vertices. I has a connection to all possible. Okay. I is in a common neighbor of S. J is in common. Okay. Now I got it right. Thank you, Praneeth.
You
I
just,
and J are in common neighbors of S. That's the right way to say it.
and you're saying that S union IJ is a clique, except like if modulo that one edge being there.
Yeah, but this is the right way to say it. That I and J are in the set of common neighbors of S, as in I and J both have all possible edges to vertices in S. They may not have edges between each other. Now does it make sense, Praneeth?
Yeah,
It's an honest question because there's a chance that I may not still be making sense.
yeah, it does.
Okay, good. All right. So good. So now I guess I actually get to make sense here. ASI. Okay, now at least because we defined it correctly, ASI, the ith row of A sub S is actually non-zero only when S union I is a clique, as in I has all possible edges to vertices in S, right? And what is the chance of that happening?
One over 2 to the T.
Yeah, exactly. 2 to the minus T, right? And so, only 2 to the minus T fraction in expectation of, rows of A sub S can actually be non-zero. Okay. And actually now, if you look at the non-zero rows, let's understand the distribution of these, non-zero rows. Okay. So if you look at, the set of common neighbors, okay, then if you look at just the common neighbors of S, then once all the rows and columns are indexed by vertices which are in common neighbors of S, then the distribution of ij is simply independent plus minus one. Okay, and so the point is that you basically gotten the same distribution except on a smaller number of vertices, right? So in expectation you have about 2 to the minus t n vertices on rows and columns, and the distribution of each entry is same as before, plus minus one, with equal probability. And so we can again apply the fact now. So applying fact yields that the size of the click is at most. Okay, so now one trick that I'm doing, or at least one bait and switch I'm doing, is that I need not only an upper bound on the eigenvalue of a sub s for a single s, I need a max over all of them. So I'm looking for like some kind of a union bound over all these spectral norm events. The fact I wrote actually doesn't allow you to do this, and that's just because I wrote the fact loosely. Oh, I guess I did not even write it correctly. I did not claim the probability of failure because it's a probabilistic event. So of course it can be bigger than root n, but most of the time it isn't. Now, one needs to be careful in the way I'm doing things right now, because I'm taking a max over all possible subsets of size t, and there are n to the t of them. So I want n to the t different events to hold together. Again, I'm not going to do the proof. This is also some more random matrix theory. Just suffice it to say that it works out in the way you hope for. So not only is the upper bound for a single a sub s true, it's actually the max of it also roughly behaves the same way. And so you can actually now get an upper bound of some 2 times t plus o of square root of n over 2 to the t from our argument. And notice that this is actually a better upper bound, right? Because for t much less than log n, actually really, because we are interested in polynomial time algorithms, t is really going to be upper bounded by a fixed constant. T is in fact, O of 1 for poly time algorithms. The first term does not really matter. It's like a fixed additive constant. And the second term is a multiplicative improvement over, the upper bound we got in the simple adjacency matrix based refutation algorithm. And so, what this allows you to do is that, so, conclusion is, so the previous adjacency matrix based refutation algorithm allowed you to work for omega, which was upper bounded by c root n for some fixed constant c. But this trick now allows you to, have a refutation algorithm for an arbitrarily small constant c times root n. So the right way to write is for all constants c bigger than 0, there exists a polynomial time refutation algorithm with omega less than c root n. Okay, does it make sense? Actually, this algorithm kind of interpolates nicely, because I think at t equals log n, it gives you it gives you the 2 log n thing back, and that's kind of good. If you, and okay, that's only true if you pay attention to the constants correctly, but if you apply it with t, which is omega log n, it gets you the right answer, the 2 log n answer that you're looking for. Okay, so it's kind of a nice interpolation between the root n bound that you can do with the simple adjacency matrix, and the 2 log n bound, which is like the truth. Good, very good. Now, before moving on, I want to tell you this matrix Chernoff bound and do a proof of this random matrix fact, the basic random matrix fact, because I want to do it again in the second half. So what I'm going to tell you by fiat is this really interesting and nice statement that you would find useful in remarkably many contexts, not just sum of squares. Okay, so many of you might have seen this before, and just bear with me for like 5 minutes. But if you haven't seen this before, then maybe you'll enjoy it. Okay, so it's a matrix Chernoff bound because it generalizes, the usual Chernoff bound that you might have seen. So if you remember what the usual Chernoff bound is, it tells you something about a sum of independent random variables which are, let's say, bounded. And so we're going to do something similar, but in the context of matrices now. Okay, so let A1, A2, so on be fixed matrices. These are not random matrices. Okay, maybe I should use a different word because we used A again. So let's call them B1, B2, fixed matrices. Okay, such that every BI has operator norm O of 1, as in the spectral norm of each BI is O of 1, and some I BI square also, well, I guess let's give it a parameter. Let's call it, let's say, some sigma square. Okay, so I've assumed two things about these BIs. These are fixed matrices. Okay, the first assumption is that each of them has largest eigenvalue upper bounded by O of 1, or largest singular value upper bounded by O of 1. These are, let's say, n by n matrices. And let's say, their variance, or this variance term, which is like the sum of squares of the BIs. So these are matrix squares, okay, has operator norm at most sigma square for some parameter sigma. Okay, then for let's call these, let's maybe even call this, so let R1, R2, etc. be independent signs. Okay, so R1, R2 are independent plus minus one random variables. Then probability that some BI has operator norm bigger than T is at most 2 times n times e to the minus t square over 2 sigma square.
You mean probability RIBI?
Yes, I do. There is no probability if I look at some of BIs. And so you're right, like this probability is over the choice of RIs. Okay, so this is, there are like several statements that kind of relate to this matrix of bound, and they hold under various assumptions on BIs, etc. So they're like many variants of them, and just like concentration inequalities that you might have used, different inequalities have different applications, and our goal is not to prove them or investigate their proofs. Our goal is to use them today, so I won't say that much about the proof of these kind of bounds. We'll just stick to this one. Okay, and maybe just given that it's 512 already, let me just sketch how you can actually get a non-trivial bound for the plus minus one random matrix we thought earlier using this Chernoff bound. Okay, so proof of weaker bound on fact in fact using matrix Chernoff. And it's really simple, right? Like aij's were plus minus one. So I want to think, I'll think of my matrix as some ij, aij, ei, ej transposed. Okay, and remember aij is the entry of the matrix. Ei, ej transpose is basically the rank one matrix, which has entry one at I comma j and zero otherwise. Okay, ei, ej just the standard basis vectors. And now let me just say that apply matrix Chernoff bound with ri equal to ai, aij's, and bi is equal to EI EJ transposed. Okay. Notice that EI EJ transposed, the spectral norm is O of 1. Well, why is this true? Well, actually, for many of these things, I can write homework 0. And so, you proved this row sum bound, which is like, the spectral norm of a matrix is upper bounded by the L1 norm of any of its rows, the max of the L1 norm of any of its rows. And so, this matrix has exactly one non-zero entry, which is equal to 1. So, in fact, it is at most 1. Good. And what about this other thing? Well, you can check if I sum over ij, actually I get a matrix whose entries are diagonals, and all of those entries are actually n. So this is n. Anyway, so now if you apply this Chernoff bound, you lose an extra log because you have to choose t large enough to kill this factor n here. But can obtain a bound of O of square root n log n this way. Okay, good. Good. Okay, very good. Okay, now what do I want to do? Oh, I guess I have some ambitious plans. Okay. Okay, so what have we done? We've designed at least 2 spectral algorithms, one better than the other, for refuting max click in G and half, right? But this class is about sum of squares, so we've got to talk about sum of squares. And so what I want to do next is spend like maybe 5 minutes telling you why actually the spectral algorithm. So people call such statements of the kind I'm going to prove as examples of the fact that spectral algorithm is, so they informally use the word captured by sum of squares. What it means, mathematically speaking, is that you can essentially always lift the analysis of your spectral algorithm and actually use it to analyze the sum of squares algorithm. Okay, so let's clarify what I mean in the context of click. Okay, what's the SOS algorithm for refutation of max click? So let's first set up so what would I do? Well, there may be multiple ways to think about it, but I'm going to think of one way which is particularly related to what we did. So, I want to write polynomial constraints on a vector x that make it a click indicator. Okay, and then try to understand what's the maximum that some xi the value can take subject to this click constraint. So what are the constraints I'll have? So I have variables x1 through xn. I'll add xi square equals xi for all I. This means that xi's are 0, 1 valued, just like always. I'll add the constraint that xi xj is 0 for all ij such that I is not connected to j. Okay. And well, that's it. Okay. That's all I want to say. I want to say that these set of constraints, x satisfies, let's call them actually script a. X satisfies a if and only if x is a click in G. Is this problematic? Is this clear? Right, like this basically, what does this constraint force you to do? You can't basically choose to assign I and j both the value 1, as in you can't choose to pick both I and j in the set indicated by x if I and j do not have an edge between them. And so this constraint forces you to always pick. So the first one just tells you that you must pick an indicator, and the second constraint tells you that the indicated set must always have all possible edges between them when you look at the graph G. Okay, good. So now I can use the following SOS refutation algorithm. Maximize overall pseudo distributions that satisfy the constraints script A. and I'm going to output this. Okay, so now two questions. One, why is this a refutation algorithm? Can someone tell me why this is an actual refutation algorithm? Why am I satisfying the correctness property that I require in my refutation? Equivalently, why is the output of this algorithm always an upper bound on the max click in the graph G?
New
Because the
subroutine.
indicator,
Yeah.
Whoa, there was a collision there.
okay, so indicator vector for the next for a click is a feasible.
Right. So there is a distribution, which achieves the value equal to max click of G, namely the distribution that outputs with probability 1, the largest click in G. And because I'm optimizing over all possible distributions, the sum of xi, I can only get something larger. Right? Good. So no matter what the degree of the pseudo distribution, this is an upper bound. Agree? Very good. So that we have taken care of. And now, what's the value of this program? What's the typical value of this program when G is drawn from G and half? Right? Like what's the omega for which this particular algorithm succeeds, right? So let's analyze it for degree 2. But it's going to be, we'll prove that the typical value is O of root n, just like, the basic spectral algorithm. And the proof is very, very simple, okay? So here is a lemma. A derives in degree 2 in variables x, the inequality okay? If this lemma is true, then I'm done because, if I take a degree 2 pseudo distribution, then I can, take pseudo expectations of this inequality on both sides and I'm done, right? Actually, let me maybe make it somewhat more fine-grained so that it makes sense for all graphs, not just my random graph. Okay? And the proof is very, very simple, okay? It's literally going to be, in some sense, it's going to be a reduction to the analysis of the spectral algorithm. And here is the proof. So let's look at, actually, you know what? Maybe I'm going to give a degree 4 proof because the proof, there is a way you can do it a degree 2 proof, but I'm going to give you a degree 4 proof because it turns out to be simpler. Okay, so what's my idea? I'm going to look at this quantity, sum xi whole square, okay? And try to understand an upper bound on it that is derived by the constraints script A. So this equals I j xi xj. Okay, good. So I'm going to separate the diagonal terms, the square terms. And here's the trick I'm going to do on the remaining terms. Whenever I is connected to j, so, I'm splitting all pairs, pairs of distinct indices into two parts. The indices where, the vertices are connected and the indices where the vertices are not connected, okay? For the first part, I write it just like this. No change at all. And let me maybe say this. And let me write this. So what I'm going to ask a funky question. What does it mean? What have I written? What is the meaning of what I have written here and why is it true? And believe it or not, I'm asking this question to you. Okay, I guess it's kind of too much to ask what does my weird notation mean. So let's clarify. What does it mean? So remember that if I take any polynomial, where is that system A? There it is. If I take any polynomial, which is rendered 0 under my constraints, then I can add and subtract it to a polynomial without really changing, so, okay. So I am trying to give a, okay, what am I trying to prove? Okay, you know what? Let me maybe be perfectly precise so that I don't do this somewhat confusing operation. Let me write it like this. Ij and okay, so well, I this was literally the meaning of the notation I was using earlier, but maybe it's just clear to write it this way. So hope this is perfectly clear, right? Like I did no really complicated manipulation. This is just literally true. This is an equality, it's a polynomial identity of on LHS and RHS. The point is that this polynomial is a combination of pairs that correspond to all non-edges. So I is not equal to j here, right? And so notice that our constraints say that each of this is supposed to be 0, right? Like I have all such pairs are rendered 0 under my constraints A. So under my constraints A, I'm actually adding a 0 polynomial, right? And so if you remember, if a polynomial is 0, so I'm using this calculus of SOS proofs where modulo the constraints A. So because I'm doing this proof under A now, I can write this as equality under A of the following polynomial. And now, because I've already discussed this too much, notice that this polynomial is exactly equal to X transpose AX for the matrix we had built earlier. Like for all edges, it has coefficient 1. For all non-edges, it has the coefficient -1. So that's exactly what it is. Okay? And now I'm going to use the following upper bound, and you will tell me why it is justified to do within this curly brackets. Why is it okay to do within this curly brackets? Why is it okay to do this step within sum of squares?
Homework 1.
Misha, did you say something?
Homework 1.
Yeah, I'm sure it's on some homework, probably homework 1. But this is an example of a spectral SOS proof, right? Like this is a, so this step uses the fact that for all matrices M, there is a degree 2 SOS proof in variable X of X transpose MX is at most. So I'm viewing this as a polynomial inequality in X. M is a constant here. And if you don't recall the proof, notice that the proof is actually really simple. It just uses the fact that, so let's maybe recall the proof. If you don't remember, this is simply, if I rearrange, then this is saying that M, the spectral norm, times identity minus M bigger than or equal to 0. And now, we are observing that this matrix is always PSD. It's a matrix of constant. There is no X there. Yeah, this is a fact about constant. This matrix is always PSD. And so PSD matrices can be written as, VV transpose for some, other matrix V. And so, it equals VV transpose. And then, this expression equals VX square, which is a square polynomial in indeterminate X. And so, I have what I've done by this manipulation is proven to you that X transpose. So what have I proven to you? So I have proven to you that M2 X square minus X transpose MX is a square. That's what I've proven to you by just like unfolding everything. And this is what we literally mean by an unconstrained SOS proof of degree 2. Good. All right, and so now we are done. That's all I'm going to say, because notice that we've basically reduced an upper bound on some xi square to a spectral bound, and oh, okay. So that's why the degree 4. So let me not worry about this cancellation business and simply write it like this. So I didn't quite derive the inequality we wanted earlier. I derived this somewhat weaker inequality. Actually, you can derive the stronger inequality too, but those manipulations are not entirely illuminating. So let me write it like this, and let me also show why this is enough. So now let's argue. Now let's say here's a lemma, or actually let me just do the manipulations. So now, if I take pseudo expectations of this inequality over all pseudo distributions of degree 4 that satisfy the constraints A, then I know that this is at most right. This is just take pseudo expectations of the lemma that you just saw, and now you will tell me why it's okay to do the next step. This is just rewriting. Some xi square is simply the norm square of x. Why is this okay to do? Why does, this line is just taking expectations of, the lemma over a degree 4 pseudo distribution. Why does this implication follow?
Cauchy-Schwarz guys.
There's only one answer, right? Like we've used this trick many, many times. So what Peter pointed out was that this is true by Cauchy-Schwarz. Actually, now can someone tell me how I applied Cauchy-Schwarz here? Just so that I am certain how it works. Oh, maybe some people are answering in chat and I'm just not looking at it. Let's see. Isn't it the opposite direction? No, it's not. Okay, so now it's time to actually do this. To what two polynomials am I applying Cauchy-Schwarz inequality?
Norm x squared and 1.
Exactly. I'm applying it to f equals norm x square and g equals the polynomial 1. And then I'm using the fact that e twiddle of fg is at most pseudo expectation 1 is 1. Pseudo expectation f squared is what you have here. And pseudo expectation fg is what you have here. Now is it absolutely clear? We use the Cauchy-Schwarz inequality for pseudo distributions. It's actually in general, whenever I'm doing these manipulations, the answer is almost always Cauchy-Schwarz. So there is a way to answer these questions without actually even thinking about them. Anywho, so now we are done, right? Because now, remember that step where we divided by x square? Well, I can do this now, except divide by e twiddle x square on both sides, right? So now if this is like star, 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 then star, star, star implies which is exactly the bound we had earlier. And now, the random matrix theory part, of course, doesn't change. Okay. So what have I done? I have captured the spectral algorithm within sum of squares. Any questions? Okay, so now, so actually, the other bound I did can also be captured within sum of squares, but we will not do that. Instead, we will go to a different example because, well, we're going to prefer variety today. But before we do that, we'll take a break. For a change, we are taking the break at about the right time instead of like half an hour late. So, we'll resume at 5:44 Pittsburgh time. We saw one example, a simple example where we studied like a refutation algorithm. Oh, I guess maybe I should make a comment before
We can't see your
proceeding.
screen right now.
I'm not sharing my screen.
It says like says you have to do like the screen mirroring thing still.
Oh, okay. Let's do it again. Now am I sharing my screen?
Yep, can see it.
Okay. Good. Actually, I forgot to mention maybe a couple points. They're all basic points, but I do want to mention them. One, it is that, we only saw a spectral algorithm, to be honest, to solve the refutation problem. But, and I won't tell you how right now, you can actually also solve the planted problem by looking at the largest eigenvector of the same matrix that we upper bounded the spectral norm of. And so what is the planted problem for the clique problem? Well, it's a so-called planted clique problem that you might have heard about. And, it's, the planted problem, it's simply the following question. You are given a graph is chosen at random, but then that's not the input that you get. A set of size omega vertices is chosen, however you want. And then, complete the clique on S in G to obtain G prime. So, some modified graph. And, input is this graph G prime. So now, if omega is bigger than 2 log n, then, in some sense, I have really modified the max clique in the graph. And this is the natural planted problem associated with the max clique question random graphs that we saw earlier. And you could ask the question of, recovering this planted clique, like recovering this added clique. Notice that it's actually has to be the unique maximum clique because, before S was added, there was no 2 log n, there was no clique of size bigger than 2 log n. And so you can use this to prove that the added clique is actually the unique maximum clique in the graph. And it's legit to ask the question of recovering this clique. And actually, you can actually solve this problem also, via a spectral algorithm that simply looks at the largest eigenvector of the same matrix A built for G prime and shows that, the largest eigenvector basically has to be very, very correlated with, the max clique indicator S. But we will not do this proof. This was actually done, in this really nice paper of Alon, Krivilovich, and Sudakov. In 98. And that's, also the best known algorithm that we have, polynomial time algorithm that we have for solving the planted clique, the search problem. Good. That was point number one. And point number two was, and this at least I can describe a proof because it is so simple, is that, given the description of both these distributions, so the planted distribution and the null distribution, what we've done already is enough to give a solution also to the distinguishing problem. And can someone tell me what that algorithm is? Like so remember the distinguishing problem, we have D planted and D null. We don't know which, but there is a sample generated from one of these distributions. And our goal is to, with high probability, correctly predict which distribution was used to generate the graph. Now I claim that, what we've done actually also gives us an algorithm to solve the distinguishing problem. And can someone tell me in one line why that is true? what is the distinguisher you would use?
Just run the refutation algorithm.
Okay, but what would you compute?
The largest, the value that it gives.
Right,
and
exactly. Yeah. So, like you'll take A of G, compute this. If this is bigger than, let's say, for omega bigger than root n, of course. If bigger than, omega, output planted. And, if this is output, null. And so this algorithm will succeed whenever, omega, the planted click, is of size much bigger than root n. And this is true simply because of the same analysis that we did, for the refutation algorithm. And so I guess one thing I want to observe is it happened to be true in our case, but actually it's more general. Refutation, whenever you can solve the refutation problem, you can also solve the distinguishing problem. Good. Now we can go to example 2. And we kind of want to do the same kind of investigation, we want to define planted distributions, null distributions, distinguishing problems, spectral algorithms, and capture them within SOS for this problem too. And my example would be refuting random CSPs. So again, this is a problem we studied earlier, but there, we only proved lower bounds. We never talked about algorithms for solving the problem. Now we want to look at this, flip side, okay? And it fits in nicely with today's goal because the refutation algorithm is going to be a spectral algorithm, okay? So as in the context of lower bounds, we're going to look at, the XOR problem. And I'll point out to you later on why that's actually, in some sense universal. It allows you to solve the problem for all CSPs, okay? I kind of hinted this even in the lower bound lecture, but, we're going to see some more details. Okay, so we're going to look at 4 XOR because evenality is nice. And how does that look like? Well, it looks like, the instance looks like, if you remember, instance looks like this. PIJKLs live in plus minus 1 and are picked at random. IJKL, they are supposed to be plus minus 1 valued variables. And the randomness, pick M 4 tuples plus, right hand sides at random and independently, and output the resulting instance. That's our model. That's our random generation process. And, we proved, at least I don't remember if we proved it in detail, but, it's some Chernoff plus union bound argument that shows that, if M is bigger than some O of n over epsilon square, then no more than half plus epsilon constraints, fraction constraints, can be satisfied by any assignment x. And so, we've gotten our distribution on no instances. Okay, so thus, if m bigger than O n over epsilon square, the above is a natural null distribution. Okay, over XOR instances. And, we can ask the refutation question. I won't even describe it in detail. Now you understand what the goal is. The goal is to take input an instance, output a value, and correctness means, as usual, that V upper bounds the fraction of constraints that can be satisfied by any assignment in X. So let me call it val of I, as before. And, the utility or usefulness is that, when I is drawn at random from D null, then, V is, let's say, half plus epsilon, or at least, strictly less than 1. Let's say 1 minus delta with probability 0.99 for some delta bigger than 0, like a fixed constant delta bigger than 0. So that's the natural refutation goal. And, you are interested in finding a polynomial time algorithm for this problem. Yeah, makes sense? Good. So now if you recall Grigoriev's theorem, and actually, why don't you recall it for me? Grigoriev's theorem, talks about this problem and the ability of SOS to solve it. And, as we discussed in the lecture on Grigoriev's theorem, we proved that, SOS of even like omega n degree does not really do anything for the refutation problem, whenever m is upper bounded by some O of n. Like whenever there are at most O of n constraints, omega n degree SOS cannot actually prove even unsatisfiability of, this XOR CSP instance. So let me maybe just say this way: there exists an omega n degree pseudo distribution that satisfies all constraints of a random 4 XOR formula. With, m at most order n. And, with probability, let's say 0.99 over the draw of the instance. Actually, if you remember in the lecture, we identified a very simple deterministic, combinatorial condition under which the refutation, like under which the lower bound, succeeds. And the condition was like this, hypergraph expansion property, of the 4 XOR or 3 XOR, whatever we did at that time instance, right? And so the probability comes in only, whether this property is going to be satisfied with high probability when you draw a random instance. Okay. So that was about sum of squares, etc. But today we want to see algorithms. And of course, we're not going to beat sum of squares today. So we're going to design an algorithm that succeeds when m is much larger. So, when m is order n, we know that sum of squares of even omega n round or omega n degree does not succeed. So today, we'll give a polytime refutation algorithm. It will be a spectral algorithm that succeeds in proving a random 4 XOR instance unsatisfiable with probability at least, 0.99 whenever m is bigger than, some constant times n square. So it's like about n times larger than, the bound at which the lower bound that we proved holds. Okay, is the statement clear? Like what we're going to do now? Feel free to stop me as usual. I have all the time in the world. You probably don't. I do. Okay, good. So let's, construct a spectral algorithm. So, let's construct so again, remember our goal? Remember how we constructed spectral algorithms? We got to make a matrix out of, the input, then connect its largest eigenvalue to, the parameter that we care about upper bounding. And then, just return the largest eigenvalue of this matrix. As long as the matrix can be built in polynomial time, our refutation algorithm is going to be polynomial time. And then we analyze, how good the bound is, right? Same steps. Good. So we're going to construct a matrix. Here is my matrix. So now this time my matrix is going to be in n square by n square dimensions. So it's going to be indexed by, all possible pairs of variables on rows and columns. And Aij KL, the IJKL entry of this matrix is going to be Bijkl over 24. Hopefully I got that right. If IJKL appears in the constraint and 0 otherwise. Okay. And why am I choosing this matrix? Well, notice the following. So consider, as usual. Oh, actually, let's maybe write like the sum over IJKL, XI, XJ, XK, XL, AIJKL. And now, help me out here. Suppose X satisfies all the constraints. Suppose X is some assignment that satisfies all the constraints, okay, of the instance I. What is the value of this expression when I evaluate it for that particular X? Okay, so let's maybe reason about it. What does satisfying a constraint mean? X satisfies a constraint, whenever Xi, Xj, Xk, XL equals Bij, KL, right? That's what it literally means by satisfying the constraint, right? Still with me? Good. So if X satisfies the IJKL constraint, then this 4 tuple is going to evaluate to Bijkl. I have Aijkl equals Bijkl over 24. So I get Bijkl squared over 24, right? Now Bijkl is a plus minus 1 thingy. So a square is always 1, right? So I'm basically adding, for each IJKL that I satisfy, I'm adding, 1 over 24 in this expression, correct? So what does it all add up to?
M.
Did you say M? Did you say M or N?
I think it's M.
Yeah, exactly. Tim is absolutely correct. Yeah. This is going to be M. And this 24 is like, okay, can you explain the reason for 24 too, Tim?
Oh, just because permutation of 4 things.
Right, exactly. The same, IJKL thingy occurs 24 times or 4 factorial times. And so, I gave them all equal weight and labeled them as 1 over 24. Okay. So good. Right. So this particular thingy is 1 if, if it is M, if, all the constraints are satisfied by X. And in general, if, let's call it X, if X satisfies all constraints, and more generally, so let's call this thingy I of X. Val I is at most half plus I of X by 2. Actually, easier for me if I normalize so that everything is 1. And now I think it's correct. So what does it mean? This is same as before that we studied in the lower bound lecture. This fraction of constraints in I satisfied by an assignment X. And the way I've set this degree 4 polynomial up here, val Ix is at most half plus I of X by 2. And why is this happening? Well, because my polynomial here basically evaluates to plus 1 if I satisfy a constraint, like a term evaluates to plus 1 or plus 1 over 24 if I satisfy a constraint. And if I do not satisfy the constraint, it evaluates to minus 1. And so if it were like if it evaluated to plus 1 and 0, then I would get the fraction of constraint satisfied. Because it evaluates to plus 1 and minus 1, I actually get the difference between satisfied constraints and unsatisfied constraints, and I just rearranged it to get this formula. Good. Which means that to refute, it suffices to prove that I of x is small. Let's say epsilon, for all x in plus minus 1 to the n. Right? Make sense? So now, I'm going to construct a spectral algorithm. And actually, I already gave you the matrix A. And I'm only going to observe that if you look at this polynomial that I wrote down over there, I of x equals 1 over m, I j k l, x I x j x k x l, a I j k l equals and remember, x tensor to the 2 is basically, the n square dimensional vector whose ijth entry equals xi xj. Okay. Does it all make sense? Feel free to stop me and ask questions if something I said doesn't make sense, but that's it, right? Like I've written I of x as a quadratic form. And if this is true, then, I can, oops, don't need a star. And actually, each entry for a plus minus 1, so the length of this x tensor 2 is going to actually be equal to n square. Length square is going to be n square because, each entry is plus minus 1 valued. Okay, everything good so far? So, once I have set this up, I have related the value of I, the instance I, to, the matrix A. So now, I have a refutation algo, which is simply, output half plus half of n square m. Okay. And by this calculation that we just did, by this sequence of upper bounds that we just did with by just basically the only inequality was this one. We've already proven that this is a correct algorithm. It always outputs a true upper bound. Yeah. And so the only question for us is how good is it? Does it all make sense? Are there any questions? Okay, I guess it makes sense. All right. So, we just have to examine what this, the spectral norm of this matrix A is to actually finish the proof, right? And so, I'm going to use this matrix Chernoff inequality that we wrote down earlier to actually analyze, this quantity. So first, so for every C equals I, J, K, L, let maybe A sub C be the following matrix. It's a really trivial operation. A sub C basically, has a +1 in any entry. If, it's row and column union out to the variables that appear in constraint C. And otherwise, all of the other entries are 0. Okay? Actually, let's make it +1/24 so that, things fit correctly. Then A equals sum over all the constraints, B sub C, where B sub C is same as Bijkl times A sub C. Still good? So now notice that, I've written my matrix as a sum of independent +-1 combinations, because B sub C is +-1 and independent for my distribution, of fixed matrices A sub C. Agree? Okay, very good. So next, what do I want to do? I have to now, analyze these, two quantities that appear in matrix Chernoff inequality. So the first was, what is the spectral norm of any A sub C? Well, it doesn't actually matter what it is, or at least it doesn't matter in too much detail what it's going to be, but you all will agree that it's going to be O of 1. Actually, the L1 norm of any row is going to be, I think, strictly less than 1. And so certainly O of 1 is a valid upper bound. Does anybody see any problem with this? For all C. Okay, very good. So no problems there. And 2, I need to analyze right? I need to analyze the spectral norm of sum of AC squares. This was the variance term, right? Remember, like this was the sigma square thingy that we wrote down in the Chernoff inequality. So what is this going to be? Let's try to analyze this, okay? So when I take the square of A sub C, so what are the entries of this matrix? So if I remember my matrix squaring correctly, it's going to be sum over Rs, A sub C, Ij, Rs, A sub C, Rs, KL. Now notice what our definition of A sub C is. It is non-zero, its entry is non-zero only when Ij, Rs actually union out to KL. So exactly one term in this summation contributes. Namely the term, well, at least maybe, okay, not exactly 2 terms in the summation contribute. And they correspond to the situation when the set Rs equals K sub L, KNL. Still good? I'm doing trivial stuff, but hopefully it's clear. Feel free to stop me. So only 2 terms in this summation contribute. And in that, oh wait, is that true?
Don't no terms contribute? Because
Actually,
if you have KL, the other thing is 0.
That's true.
No, I think it should be I prime, J prime, K prime, L prime, because you want to distinguish them from C. Right?
Sorry, what?
Oh, the Ij, KL that you wrote down are not equal to C, I think.
Right, exactly. Yes, you're right. Like I'm confusing myself in the notation. So let's call it RSTU. And I need more letters. VW, I guess. Okay, so this is going to be sum ACRS VW VW TU. And the sum is over all V and W. Okay? So I think what we already did, or what we were already thinking earlier, implies that if So observation, if RS I've confused myself. Let's see. When is this non-zero? I see. Good. No problems. Okay. So this is non-zero. So a term is non-zero only if, RS equals TU. Okay. And RS is a subset of IJKL. Now that I've made a claim, tell me if you disagree with me. Tell me this does not make sense. I'm saying that's the only situation that actually, these terms actually contribute a non-zero value. Right? Like imagine that if RS and TU are different. In order for us, to have a non-zero value, RS better be IJ, and let's say TU better be KL. I mean, any other pair would have been fine, but let's say, RS equals IJ and TU equals KL, for example. But in that case, there is no VW that will make both those terms simultaneously non-zero. Right?
It can also be UT, right? RS equals UT. So
say it again.
Can also be RS
Yes,
equals
yeah.
UT.
This is equality
Yeah.
of sets. You're right.
Oh.
Absolutely. Okay. Make sense? Okay, very good. So if it makes sense, now we can, go ahead and analyze what happens to AC square, the sum. Okay. So the entries of sum of AC squares is indexed by pairs, right? And so now, I guess I need to observe in particular. So in particular, this implies, okay, I should have observed. So in particular, AC square is, okay, I can't quite say it's diagonal unless I, okay. Okay, sorry, I have to modify my proof a little bit. I need to make these things sets and not ordered pairs. Sorry about that. Which would mean that this 24 would be somewhat different. So let's maybe call it some other, what would it be? I think it will be 6. I'm sorry. Yeah, I just want to make A indexed by sets of size 2 rather than, ordered pairs. This is because, I want to, so the reason is that I want to conclude here that AC square is a diagonal matrix. And I can't quite do that if, I can interchange the order of TU. Anyway, it doesn't really affect any of what we did earlier, except that in this calculation, because I want to interpret AC square as diagonal, it's useful to think of AC as, or AC and both A as indexed by sets of size 2 rather than, ordered pairs of size 2. In that case, you would agree that because the entry of AC square is non-zero only when the set RS equals TU, AC square is a diagonal matrix. And now if I look at the sum over all constraints of AC square, then, I'm going to look at basically, what are its diagonal entries. And the diagonal entry, so, is also a diagonal matrix because It's a sum of diagonal matrices, and its entries I want to claim with max entry equal to O of m over n square plus O of 1. Maybe I should have some log n for a union bound. So why is this? So look at the ijth entry, right? For every constraint that the pair ij is in, I can get, a non-zero entry in the diagonal corresponding to the set ij, right? And whenever there is an entry non-zero, it is O of 1. Like, it doesn't matter what that constant is, 1 over 6, 1 over 24, 1 over 1, what doesn't matter. It's some O of 1 quantity, right? And now I'm going to gain a diagonal entry in every set ij whenever, for every constraint C that contains the pair ij. And so the question is, how many constraints, contain the pair ij of variables? Now, each constraint was chosen uniformly at random and independent. So in expectation, the number of constraints that contain a given pair is going to be m over n square, right? Because I've fixed a pair of variables. So, I lose 1 over n square because of that. And now, if I do a union bound, you would imagine that, with high probability, I will not have more than some m log n over n square thingies. Now, sometimes, and so I'm adding this O of 1 because, that's always, that's, some entry is always going to be, some entry is always, okay. So let's maybe be a bit slower. Fix any ij. Then number of constraints containing ij is O of m log n over n square plus O of 1 with high probability. That's the claim I'm making. That's the claim I was justifying earlier. And I guess maybe I need to make this one also order log n. This is certainly an upper bound. If now, okay, so if this is the upper bound I use, hopefully this is clear, then, because, so now since some AC square is diagonal, the largest eigenvalue of some AC square is at most the max entry on its diagonal. And that we just established as order m log n over n square plus, let's say, order log n. Okay, so now, we are doing very well, because if we now apply the matrix Chernoff inequality, then we can prove that some AC is at most. So actually, let me recall and then apply it. So remember, the inequality was that some AC is bigger than equal to some parameter t with probability dimension of the matrix. So that's n square 2 times e to the minus t square over sigma square, where sigma square, is this quantity we computed above. And so, in order for me to make this quantity like, let's say, 0.99, I need to choose t, which is, sigma square log n up to constants, which means that, the bound I get is at most, let's say, sigma square. So let's say m log square n over n square plus log square n with high probability. And, because we are shooting for a result where m is bigger than, much bigger than n square, the second term won't count. And so, when m is bigger than n square, first term dominates. Very good. And now we are, oh, sorry. When t is, sorry, I think I messed up again. I have a square there, so I need just this, and it's actually important. Okay, very good. So let's make sure, you know, that given that I made lots of back and forths here, let's make sure that you all agree. How was the argument? We first wrote our matrix, which is now indexed by sets of size 2, as sum of these matrices A sub C, right? A sub C are fixed matrices, okay? And they are scaled by this random, you know, plus minus 1 independent random bits, okay? Then to apply matrix Chernoff, I need to confirm that the operator norm of each AC is order 1, which is true, you know, just because only a constant number of entries in A sub C are non-zero. And the largest constant that appears in the entry is like, I don't know, at most 1. And the other quantity that appears is this so-called variance term, the sigma square term, which was the largest eigenvalue of sum of AC squares, right? That's what we did some effort to estimate. We first confirmed that when I square A sub C, then it's a diagonal matrix. And this was because, you know, the thing is an entry is non-zero only when RS equals TU. Therefore, some AC square is also diagonal. And if I want to, you know, upper bound the largest eigenvalue of a diagonal matrix, it's going to be equal to the largest entry, you know, it's the largest entry that appears on a diagonal, right? That's what the largest eigenvalue of a diagonal matrix is. So I need to estimate what's the largest diagonal entry. Now, if I look at the diagonals of some AC square, they're indexed by sets of size 2. And each constraint that contains that set contributes a constant to the diagonal corresponding to ij. So in order to upper bound the diagonal entries of AC square, the sum, I need to calculate the number of constraints that contain a given pair of variables I comma j. Okay. Now, you know, for any fixed ij, the expected number of constraints that contain ij is m over n square, right? And think of m as much bigger than n square. So then this is a non-trivial and reasonable quantity. Okay. If I do a union bound over all possible pairs, there are n square of them, right? Then I'm going to get an upper bound of m log n over n square on this, largest diagonal entry, which is also an upper bound on the spectral norm of some AC square. Okay. So this means that we have estimated this sigma square to be about m over n square. Forget about the second term because it doesn't matter when we are looking at m bigger than n square. Okay. So now, let's look at this inequality, the matrix Chernoff inequality. I need to make t square bigger than sigma square log n, or like sigma square 100 log n, in order to kill this n square that appears in front. And to make this expression, let's say 0.01, so that the upper bound I get is like true with 99% probability then, right? Well, that requires me to take t square, which is bigger than sigma squared log n, or t bigger than sigma log n, sigma root log n. Okay, so that's this claim here. And so now, we are done because sigma square was basically m log n over n square. So sigma is root m over n times, let's say, log n. I guess, did I mess up log n? Doesn't matter. What I'm going to do is ignore the log factors, because I'm not even trying to optimize them. Okay, so that's the upper bound I got, on, that's the upper bound I got, which is true with 99% probability on some AC, this matrix that I care about, which is equal to A. And so now, remember when we proved, so, so if we go back to our refutation upper bound, we get a bound of val I is at most half plus half m, sorry, what did we get? N square over m times the operator norm of A. That's the bound we wrote down earlier. And we've come up with an upper bound of root m over n up to log factors. So this upper bound is half plus half n square over m root m over n. And let's say polylog terms. So and now, this is less than half plus, let's say, epsilon if m is bigger than O tilde n square over epsilon square. Okay, lots of calculations, but did it make sense? This argument makes sense. It's just a application of matrix Chernoff. In some sense, this is one thing I wanted to show you is that, you can do, you can do a lot with just the matrix Chernoff inequality. And of course, there are better ways. There are other ways to bound the operator norm of this matrix A. And, these other ways don't even need these tricks where I was playing, where I wanted to think of them as indexed by sets and not pairs. So there are like other tricks, somewhat more complicated tricks, which you can use to upper bound a spectral norm of such matrices. And, they even give you better bounds, as in like they don't lose log n factors. But I wanted to show you how this black box inequality is actually very good for us. Right. And so it's kind of useful because you can use this inequality in several places and you don't have to do anything, problem specific computation. So hopefully this proof was somewhat useful. And we succeeded in getting a refutation algorithm that works whenever m is bigger than like up to polylog factors, just bigger than n square. Now notice again that this bound is a factor n higher than the information theoretic minimum. Right, like when m is just n over epsilon square, we know that the true value of the instance is half plus epsilon, but we require n times more constraints in order for a polynomial time refutation algorithm to exist, right? And so we already used a word for this phenomenon. This is yet another example of an information computation gap. In particular, there is no polynomial time algorithm that succeeds in refuting random 4 XOR when m is less than, let's say, n to the 1.9999. No known polytime refutation algo that succeeds when m, let's say, is n to the 1.999. Actually, there is no known refutation algorithm that succeeds even when m is at m is n to the 2 minus little of 1 for any little of 1. So if I give you a random 4XOR instance where the number of constraints is strictly asymptotically smaller than n square, then we do not know of any polynomial time algorithm. And so in that sense, what I've actually given you up to polylog factors is actually optimal in terms of the best known algorithm. Now, again, like this other algorithm that we built in the case of Click, you can actually build somewhat more clever matrices and get an arbitrarily small constant times n square. It requires more effort here, but it can be done. Okay, we will not do that today. I guess our purpose was to just note that we've come up with yet another spectral refutation algorithm. And to the best of our knowledge, this is also the best known. This is literally the best known algorithm for refuting random 4 XOR that we know of. And it exhibits a gap from this information theoretic minimum threshold that we know of in this case. Good. So, are there any questions before I go ahead? Okay, good. So let's do the same stuff that we were doing earlier, okay? Let's define a planted model. Oops. And so, remember we started with this GN half distribution, and then we produced a distribution on, graphs with added clicks. In the same way, we want to start with random CSP distribution and now produce an instance, where constraints are satisfiable. Okay. So how would I do that? So here is a planted model. It has a parameter m. So pick m 4 tuples at random. Pick arbitrary x star. So remember, in the context of the planted click problem, I had, chosen some fixed set of vertices to become the maximum click. And so same way, I'm going to use x star to be, my planted assignment. I'm going to make an instance where x star satisfies all the constraints by fiat. Maybe I should write the star at the top so that I can write indices. So basically, I am choosing the right-hand sides of these equations in order so that x star satisfies them. Okay. And so, this is my planted assignment. And so all of you see that the instance I have so produced is going to be satisfiable? In particular, all the constraints can be satisfied by the assignment x star. Is that clear? Okay, very good. And so, so that's a planted that's a planted model. And so, given a planted model, I can ask, can you find and what's the answer to this question?
Yes.
And why is that?
Gaussian elimination and is elimination.
Right. Okay. So exactly. So that was a trick question. I can actually solve this problem, no matter what m is, because as long as like m is bigger than n, x star would actually be the unique solution to the system of 4 XOR equations, which are linear equations over the binary field. So I can do Gaussian elimination to solve them, which means that in here, if I literally plant an assignment to satisfy all the constraints, the problem is going to be easy. Okay, as in, I can indeed find a planted assignment easily. I can find a planted assignment easily, even when m is much smaller than n square. But it turns out that I can modify this model just a tiny bit and make it somewhat hard. So choose RHS to be this with probability, say 0.99, and minus, meaning disagree with probability 0.01. So, basically now I have introduced tiny bit of error in every constraint. And you can prove that, x star is still the best assignment, but it of course doesn't satisfy all the constraints. It satisfies only 99% of them. So it turns out that for this problem, we do not know of any algorithm that can find x star when m is much less than n square. But what if m is much bigger than n square? Well, it turns out that in that case, there is a polynomial time algorithm. And just like in the case of planted click, it can work with this matrix A that we generated, take its top eigenvector, and show that it's actually going to be close to x star. Okay, so there is a spectral algorithm that will succeed. And just like the click problem, if I now focus attention on the distinguishing variant, then we have an immediate solution because, as long as m is bigger than n square, our eigenvalue upper bound certifies that the instance is unsatisfiable in the null case, while it's always going to be 99% satisfiable in the planted case. Okay, very good. So, we've basically seen two examples. And given that there are only 10 minutes, I will not go to other CSPs, but I'll just mention that you can reduce other CSPs to XOR. Okay. So in some sense, what we did is actually kind of universal. You can reduce every CSP to XOR and then use the spectral refutation to refute XOR. So you can actually refute every CSP in the right way by this trick. Let me not go into, the details of this. Let me instead, talk about somewhat more high-level conclusions. Oh, and let me also maybe mention another thing which I will not do, which I did for click. So, can capture this spectral algo within SOS in a similar way. Okay, so now we've seen two examples. So let's maybe see what's common between the two examples. We started with a refutation problem. We solved it using a spectral algorithm. We proved, that this is captured within SOS. We also, happen to have essentially optimal algorithms or essentially best known algorithms. There was some relationship to planted problems. And, especially the distinguishing problem. And actually, it was only one-way relationship, So we saw that spectral or any refutation algorithm implies distinguishing, implies an algorithm for the distinguishing problem when under whatever constraints, the refutation algorithm exists. So that's kind of a summary of what we saw. So what I want to tell you is maybe a somewhat surprising result, which actually gives you a converse of this whole relationship. So let me maybe, so maybe summarize this discussion so far. Spectral refutation implies sum of squares. Refutation implies, distinguishing. So here is a theorem. It's the last thing I'm going to tell you today. And it says that, for a, so it's going to be somewhat vague, but both the problems we studied today fit into this large class. So this, so what we studied so far is, we showed spectral refutations. We invented the right matrices to play with, by some trick, right? Like we just happened to get lucky. The natural matrices happen to give us, basically, essentially the best known algorithms. But what we did was like we picked these matrices and did some analysis to show that the largest eigenvalue of this matrices gives us a way to refute non-trivially both these kind of questions that we studied today. And then we observed explicitly in the first case and just hand wavy hand wavy explanation in the second case that both these refutations can then be used to actually argue that even SOS succeeds. And this is what we said is referred to as capturing the spectral refutation within SOS. This theorem is saying that in some sense this methodology is complete. This theorem is saying that for a large class of problems, whenever there is any way to use degree D SOS to do refutation, then there is also some matrix. I don't know what matrix that is, probably not as simple as the ones that we saw today, but there is a matrix whose size is roughly n to the O of D by n to the O of D. Further, the entries of this matrix can be computed efficiently. In particular, they are simply going to be order D degree polynomials in the input. So, for example, in the first example that we saw today, the input, was the edge indicators, whether an edge is present or not. And so, the entries of this kind of a matrix in that context would be, degree D polynomials in this edge indicator variables. In the second case, it would be degree D polynomials in this BIJKL variables, if you will. Okay. But basically, there is some matrix whose dimension is n to the O of D by n to the O of D, whose entries are degree D polynomials. Therefore, you can construct this whole matrix in n to the O of D time, given the input. And the spectral refutation algorithm, which simply is going to take the max eigenvalue of this matrix, would do just as well as the degree D sum of squares algorithm. Okay. So in other words, what we are saying is that at least for a large class of refutation problems, and therefore also therefore like distinguishing problems, sum of squares is no more powerful than spectral refutation algorithms. So of course, I'm not going to prove this theorem to you, but this was this was the last point I wanted to make in the context of what we did today. All right, yeah. So this is all I want to say today, and next time. So today we saw this relationship between sum of squares and spectral algorithms, which were like a simpler special class of algorithms. In the very last lecture, we'll study relationship of SOS to yet another example of a simple class of algorithms. This time it will be even simpler than spectral algorithms. These algorithms will simply compute low degree polynomials of data. They won't even like play with eigenvalues. And we'll see, what's the relationship with algorithms that simply compute low degree polynomials of inputs. How powerful can they be? And what is the relationship to SOS in the context of average case problems in the next time. Good. All right. So yeah, we can discuss questions.
So can you construct this matrix?
Say it again.
Like let's say you have an SOS refutation algorithm. Can you
Good.
construct this matrix?
So okay, that's a good question. So in general, so this theorem holds for basically a large class of problems which have certain noise robustness property, but it's not worth defining it right now. So let's maybe just leave it at that. So in general, this theorem is non-constructive. But essentially, in every example that we study, we can, with some work, explicitly come up with these matrices. So let me, give you a somewhat surprising consequence of this fact. So remember the tensor decomposition algorithm that we studied earlier? So we use the sum of squares algorithm, right? What you can do with this, I mean, in some sense, you didn't need to know all of this for doing that. But, one nice consequence of this is that you can extract from the SOS-based algorithm, you can extract a simple spectral algorithm that does the same thing. as in it succeeds in tensor decomposition, you know, just as well as the sum of squares algorithm.
Wait, is there a tiny gap in the overcomplete region?
So the gap occurs because you are not just extracting a spectral algorithm there, you're extracting a much faster spectral algorithm. So right now, you know, there is no theoretical saving of running time, right?
Mhm.
Like the running time of both the algorithms is going to be n to the O of d, even though, you know, for whatever practical considerations, you would prefer a spectral algorithm over solving semi-definite programs. What you are observing, Jeff, is that in the context of tensor decomposition, you can actually speed up this spectral algorithm. You can actually make a, you know, extremely fast spectral algorithm, almost linear time algorithm, and that requires some additional assumptions on, you know, components of the tensor. And so, you know, if you know, if you were looking, for example, for, you know, extremely fast practical algorithms, then this class must have disappointed you. But I suppose this is a tiny ray of hope over there. It's like it turns out that this step is almost generic for, you know, essentially all the problems we've looked at so far, you know. But then it turns out that in many cases we can, so this is generic, but, you know, existential, like as in we don't quite know what spectral algorithm it is. But in many cases, we can extract that algorithm explicitly. And then, in fact, you know, in some cases, we succeed in even speeding it up. As in, you know, we can extract extremely fast practical algorithms using the whole machinery. Okay, that's my answer to your question, Tim.